Good morning everyone. In the last lecture, we have discussed the graphical method for solving linear programming problem for which the constraint that involved both type of inequality. That means we have a greater than or equal to or less than or equal to signs among the constraints. So we considered the maximization of problem in the last lecture where we considered the both constraint, which is generally known as it is mixed constraint example. Now we are going to consider the minimization problem as against the maximization problem which we are discussed in the last class. Now we have a minimization problem by considering the mixed constraint, that is we have a greater than or equal to sign and less than or equal to sign. Both are there present in the given constraints. Therefore, we will consider how to solve the linear programming problem with mixed constraint which include both less than equal to or greater than equal to signs in the given constraint. So let us consider one problem. See, a firm want to produce two products, that is product X and product Y. The daily production upper limit is 600 units of the total production. But at least 300 total unit must be produced every day. So machine as consumption per unit is 6 for commodity X and 2 for commodity Y. And at least 1200 machine hours must be used daily. See, manufacturing cost per unit of are rupee 50 for the commodity X and rupee 20 for commodity Y. See, here our problem is related to the, firm wants to minimize the cost and solve the linear programming problem graphically. So from the given information, many information are given here, and out of that we have to capture all this information, especially by considering the objective problem and at the same time, what are the various constraints. See, the first thing we are going to identify here, what are the decision variable here. See, we have two commodities which are producing here. So commodity X and commodity Y will become our decision variable. So X and Y are the decision variable. After identifying the decision variables, then the next step is to find out the objective function. See, in the given problem, it is already mentioned that firm wants to minimize cost. So our objective function is related to the minimization of cost. So here we want to minimize the cost, and the cost is already given here. For the commodity X, see, manufacturing cost per unit is rupee 50 for the commodity X and 20 for commodity Y. So by using this particular information, we are going to frame the objective function, that is minimization of cost, that is C is equal to 50x and 20y. So I am writing here our objective function as 50x plus 20y. See, after identifying the decision variable and specifying the objective function, the next step is to frame the constraint. So what are the various constraints here? See, we are going to consider various constraints. See here, the first constraint is related to this particular point, that is daily production upper limit is 600 unit for the total production. So that means that X plus Y, that means by considering both commodity, the maximum limit, upper limit is given, that is 600. So I am writing here that is the maximum limit, the both commodity can be produced 600, not more than that. So here the inequality sign, see, it is less than or equal to 600. So that's why, see, the statement should be very clear. See, daily production upper limit, that means maximum limit, not beyond that particular limit. So that's why we are putting the sign, it is less than or equal to 600. Now, but there is another sentence, that is, but at least 300 total unit must be produced every day. So this is also another constraint. That means both commodities are minimum of both commodity, that is, it should be at least 300. So here I am going to consider X plus Y, that is greater than or equal to 300. Why it is greater than or equal to 300? See, at least 300 total unit must be produced, not below that. So at least 300 units must be produced. So I am going to consider here the inequality sign which is greater than or equal to 300. So minimum 300 unit must be produced. Then another information, machine asks for the consumption per unit is 6 for commodity X and 2 for commodity Y. And at the same time, at least 1200 machine hours must be used. At least must be used. So here it will become, see, 6x plus 2y which is greater than or equal to. So because why it is here? It is at least 1200 machine hours must be used daily, not below that. So it will become, see, the another constraint, that is it will become 6x plus 2y which is greater than or equal to 1200. Okay, so 1200, we are writing here this particular constraint, that is 6x plus 2y which is greater than or equal to 1200. So we have an example of a mixed constraint here. See, one of the constraint that is less than or equal to, and the remaining two constraint are sign are here, see, it is greater than or equal to. Okay, so we have an example of a mixed constraint, and at the same time our objective function here, we want to minimize the cost. So here we are going to specify that our non-negativity constraint also, that is the decision variable, that is x and y, must be greater than or equal to 0. Now I am going to write this mathematical formulation of linear programming from the given problem, that is our objective function is minimization of cost, and we want to minimize c is equal to, that is 50x plus 20y, which is subjected to the given constraint. These constraints are x plus y which is less than equal to 600, x plus y which is greater than or equal to 300, and the third constraint, that is 6x plus 2y which is greater than or equal to 1200. Now by considering this particular constraint, we have of course the non-negativity constraint are also there. That means the decision variable x and y should be greater than or equal to 0. Now our mathematical formulation of the linear programming problem is already completed. The next step, we want to find the solution for the given linear programming problem. So here it is the minimization cost. So here the another step, that is we want to construct the graph for the each and every constraint by identifying its various coordinate points. So here I am considering the graph by taking the commodity x along the x-axis and commodity y along the y-axis. See, the first constraint I am going to consider here, which is equal to x plus y which is less than or equal to 600. Now I am going to convert this particular inequality sign into the equality sign. So it will become, see, x plus y is equal to 600. Now considering this particular equality sign, so we can solve this particular equation by assuming the value of y is equal to 0. So when assuming y is equal to 0, then the value of x is equal to, see, x plus substituting y is equal to 0 is equal to 600. Simply we can say that x is equal to 600. So we have a one coordinate, that is when the value of y is equal to 0, then the value of x is equal to 600. Similarly, by assuming the value of x is equal to 0, then what is the value of y here? The value of y is equal to, it is x plus y is equal to 600. So substituting x is equal to 0, then y is also 600. So we have another coordinate point of the given constraint 1, that is when x is equal to 0, then the value of y is equal to 600. Now, see, I am going to plot these two coordinate points on the given graph. So here I am going to take the particular scaling point, that is from the 0 to 600, because the maximum point here it is 600. So I am going to consider the scaling point up to the 600. So here the x is equal to 600 when value of y is equal to 0. So it will be this point. So I am denoting this particular point here, and when the value of x is equal to 0, the value of y is equal to 600. So I am going to joining these 2 points, that is 600 in the y-axis and 600 along the x-axis. So I am going to draw the line, that is the red line, which is showing the first constraint, that is x plus y is equal to 600. So after graphing the first line, see, the next one we are going to consider the second constraint. So the second constraint was, see, it is x plus y which is greater than or equal to 300. So I am going to convert this inequality sign into the equality sign. So it will become, see, x plus y is equal to 300. Now by considering this particular equality sign, now we have a proper equation model. Assuming y is equal to 0, then what is the value of x? See, it will become x plus 0, which is equal to 300. We can simply say that x is equal to 300. So when the value of y is equal to 0, value of x is equal to 300, which is the one of the coordinate point of the constraint number 2. Similarly, by assuming the value of x is equal to 0, then what is the value of y here? See, the given equation, that is x plus y is equal to 300. So substituting x is equal to 0, y is equal to 300. So another coordinate point of the given constraint number 2, which is equal to 300 when x is equal to 0. So now I am going to plot this particular 2 coordinate points from the given constraint number 2 on the graph. Then it will become, see, one is here, that is when x is equal to 0, then value of y is equal to 300. When y is equal to 0, then the value of x is equal to 300 here. So I am going to join these 2 points, that is 300 of y axis and 300 of x axis. So it will be representing by using, it's a blue line. So it is representing for the second constraint, that is x plus y, which is equal to 300. Now again we have one more constraint also there. So I am going to consider the third constraint, that is constraint number 3, which is equal to 6x plus 2y, which is greater than or equal to 1200. Now again I am going to convert this inequality sign, that is greater than equal to, into the equality sign. So it will become, say, 6x plus 2y, which is equal to 1200. Now here by assuming the value of y is equal to 0, then what is the value of x here? See, 6x plus 2 into 0, which is equal to 1200. So this term will become 0, then 6x is equal to 1200. Then dividing the both side of the equation by using 6, it will become x is equal to 1200 divided by 6, which is equal to 200. So when the value of y is equal to 0, then the value of x is equal to 200. Similarly, by considering x is equal to 0, then what is the value of y? See, when x is equal to 0, then the value of y, see, will become 6 into 0 plus 2 into y. So this term, that is 6 into 0, will become 0. Then 2y is equal to 1200. By dividing the both side of the equation by using 2, then this will become, see, it is y is equal to 1200 divided by 2, which is equal to 600. So our coordinate points from the constraint number 3, that is when y is equal to 0, then the x is equal to 200. When x is equal to 0, then value of y is equal to 600. Now I am going to plot these 2 coordinate points of the given constraint number 3 on the given graph. Then it will become, see, I am going to identify the points here. See, it will become, one point is here, it is 0. When x is equal to 0, the value of y is equal to 600. When y is equal to 0, then the value of x is equal to 200. So I am going to identify this particular 2 points. Then I am going to draw a particular line representing these 2 points, that is representing by using a green line. So here this green line is actually representing for the constraint number 3, that is 6x plus 2y is equal to 1200. Now we are plotted the 3 constraint line. We want to identify, feasible region. So the next step is identification of the feasible region. Of course, we know after drawing these 3 lines, which is actually representing for the 3 constraints, the next step is to identify the feasible region. And the feasible region, which is bounded by the constraint line, and all the point inside the feasible region, or all the point which are bounded of the feasible region or at the corner point of the feasible region that satisfy our entire constraints. So at this particular point, we have 2 constraints which are having greater than equal to sign. See, what are these 2 constraints? See, x plus y, which is greater than equal to 300, and another one, that is 6x plus 2y, which is also greater than equal to 1200. So if you go for considering these 2 constraints, that means 2 constraints have greater than or equal to type constraint. Hence the feasible region will be above of these 2 lines, above of green line and the blue line. So we have area that is above this green line, see above this blue line also. And one of the constraint, that is we have less than or equal to the type that is representing x plus y, which is less than or equal to 600. So we are going to consider, see the feasible region here, it will be below or it is the left side of the red line or red constraint line. So hence the feasible region here, it will become, see, this will be our feasible region. This shaded area can be considered as the feasible region here, and hence the feasible region can be identified as it is the point A, B, C and D. These are the various corner points. So here finally here we can say that this shaded area is called the feasible region, or it is the solution that phase given the linear programming problem. So any point inside this particular region or this shaded area called a feasible solution will be feasible solution can be found in this particular the optimal solution can be found in this particular feasible region. So here we have a 4 corner points, that is A, B, C and D. So here the feasible region are identified as A, B, C, D. So after identifying the feasible region, now we want to identify the optimal solution among the feasible region. So the graphical solution can use it to find the optimal solution of a given problem. So here we are going to find out the optimal point as a final stage of finding out the solution for a linear programming problem. So any point in the feasible region that give the maximum or minimum point value is considered as the objective function here, which will consider as an optimal solution. In our case, it is the objective function was the minimization, of course. So we want to identify such a point where the cost is minimal. So in the feasible region we can see here, there are many points that satisfy given constraints simultaneously, but see that is A, B, C and D. But see how to find or how to get the minimum value of the objective function, that is generally considered as the optimal solution. So optimal solution will be lies at the one of the vertices or the corner point that may be A or maybe B or maybe C or maybe D. So out of this particular point we want to find out what actually the optimal or the final solution is. So I am going to write these particular various vertices or the corner points, that is A, B, C, D, along with their values. See at the point A, see at this particular point, what is the value of x, which is equal to 0? What is the value of y, which is equal to 600? So I am going to write here at the point A, x is equal to 0 and y is equal to 600. Similarly, at the point B, see at this particular point B, the value of x is equal to 600. And what is the value of y? Y is equal to 0. So here I am denoting here at the point B, x is equal to 600 and value of y is equal to 0. What about the C? At this particular point the value of x is equal to 300 and the value of y, which is equal to 0. So at this particular point C, x is equal to 300 and the value of y is equal to 0. Similarly, we have the last point, which is the point D. At this particular point, we have to find the solution of the intersection of these two constraints, that is one is 6x plus 2y which is equal to 1200 and another one is it is x plus y which is equal to 300, because these two lines are intersecting. So we have to solve these two equations simultaneously, because we have two unknown variables here, that is x and y, and we have two equations as well. So that if you find the solution for this given simultaneous equation, that will give the point of x and y at the point D, at this particular point. So first we are going to find out the solution for this simultaneous equation, and at this particular point D, the two equations are 6x plus 2y which is equal to 1200, x plus y which is equal to 300. So we are going to solve this particular equation simultaneously. So it will become, see, the 6x plus 2y is equal to 1200, which is the equation number 1, x plus y which is equal to 300, which is equal to equation number 2. Now by considering these two equations, we can solve this equation by using the elimination method, or you can also use this direct substitution method. I am going to use the elimination method here by multiplying the equation number 2 into 6 so that the coefficient of x can be same and we can accordingly eliminate the variable x. So I am multiplying here the equation number 2 into 6, then 6 into x which is 6x, 6 into y which is 6y is equal to 300 into 6 which is equal to 1800. So I am going to write here it is 6x plus 6y which is equal to 1800, which is considered as the equation number 3. Now considering the equation number 3 and equation number 1, see the coefficient of x is same. So if you go for subtracting equation number 1 from the equation number 2, then 6x minus 6x will be cancelled out. Then 6y minus 2y which will become 4y. 4y which is equal to 1800 minus 1200 which is equal to 600. So by dividing the both side of the equation by using 4, then it will become 600 divided by 4 which is equal to 150. So the value of y is equal to 150. So when the value of y is equal to 150, we can substitute the value of y in the equation number 1 or 2. Here we are going to substitute in the equation number 1, that is 6x plus 2y is equal to 1200. So I am substituting here the value of y is equal to 150. So it will become 6x plus 2 into 150 which is equal to 1200. So if you go for simplifying it, 6x is plus 2 into 150 which is equal to 300 which is equal to 1200. Now we are going to subtract the 300 from the both side of the equation so that 300 can be cancelled out. It will become see 1200 minus 300 which is equal to 900 here. Now we are going to divide the both side of the equation by using 6 so that we can cancel out, we can cancel out here's coefficient of x, and accordingly we can isolate the variable x. So here x is equal to, by dividing the both side of the equation by using 6, it is 900 divided by 6 which is equal to 150. So here the value of x is equal to 150 and the value of y is also equal to 150. So I am going to substitute these two values here because so that we will get the value for x and y at the corner point D. So at this particular point, that is corner point D, the value of x is equal to 150 and the value of y is equal to 150. So all the values are estimated here at different corner points, that is A, B, C and D. So now we want to find out optimal solution among these various feasible solutions. So for that, we are going to find the optimal solution, that is we are going to substitute the value of x and y of the different corner points on the objective function here. See, we know the objective function here, it is the minimization of cost, that is c is equal to 50x plus 20y. So here we have x and y variable, we are going to substitute for x and y different values at the corner points of A, B, C and D. See, at corner point A, x is equal to 0 and y is equal to 600. We are substituting here, then it will become c is equal to 50 into 0 plus 20 into 600 which is equal to 12,000. Okay. Now similarly we have the point B. At the point B, x is equal to 600 and y is equal to 0. Now we are going to substitute x is equal to 600 and y is equal to 0 on the objective function, that is here it is cost function, that is equal to 50 into 600 plus 20 into 0 which is equal to 30,000. So the third point, that is point C, x is equal to 300 and y is equal to it is 0. So if you go for substituting the value of x is equal to 300 and y is equal to 0, then the objective function will become C 50 into 300 plus 20 into 0. So if you go for simplifying it, then it will become 15,000. Similarly, we have a last point, that is point D. At this particular point, the value of x is equal to 150 and the value of y is equal to 150. We are going to substitute these values on the objective function, then it will become c is equal to 50 into 150 plus 20 into 150 which is equal to 10,500. It is 10,500 here. See, we have various feasible solutions are there, and accordingly we are calculated the value for the objective function. Now which among these particular objective function values we should take as an optimal solution is entirely depending upon what is our objective function. See, in the given function or given problem, our objective function is nothing but it is the minimization of cost. So we have to select such a value that is the least among the given estimated value for the objective function, that is the lowest value will be considered. So here the lowest value is 10,500. So here I am marking here the 10,500 is the lowest value of the objective function, because our objective function is to minimize the cost. So we can't consider the higher values here, or we can't consider the maximum value here, because objective function is nothing but it is the minimization of cost. So we will select the lowest value among the various feasible solution. So it is the 10,500. At this particular point, see, the value of x is equal to 150 and the value of y is equal to 150. So here we can write our optimal solution is lies here, and the minimization of course, that is c is equal to 10,500 here. And in order to minimize the cost, here the commodity x can be produced or consumed. Here it is 150, that is number of unit of x which is equal to 150. Similarly, the number of unit of commodity y which is equal to 150. So in this way, we can find the solution of linear programming problem graphically when we have a minimization of cost with mixed constraint, that is when we have a greater than or equal to or less than equal to constraint signs are there. So in the next lecture, we will consider the concept of duality, where we will discuss how to formulate a dual problem. So we'll see in the next lecture. Thank you.